Okay, so let's say we have this here, this chemical reaction. So how would I do it?
You write down the elements.
You write down the elements. Oh, so there's a question is, so where do I send these test corrections? You don't send them to my email. You're going to upload them. There's going to be a section that says test corrections or exam corrections. You're going to upload them there. And so you're going to get one opportunity to upload. So anything that else is uploaded, then, and usually I grade those like the very end, you know, so then you'll get those points. And it'll kind of keep you in suspense a little bit, but it'll make you work harder for each of those exams. Okay, so we put the elements down. So how many carbons do we have?
2.
Maria, how many carbons do we have on the
2.
reactant side? We have 2. And on the product side?
2.
Is there 2?
Oh no, 0.
So if there's no number there, it's assumed to be 1, right?
Okay.
Okay, so how many hydrogens do we have on the reactant side?
4.
And on the product side?
2.
Okay, how many oxygens do we have on the reactant side?
4.
And on the product side?
1.
3.
I mean 3. I didn't see that one.
Yeah. Okay, so is that balanced?
No.
No. So we need to figure out a way of balancing it. So how can we balance it?
That's where I don't know. I get stuck.
You can put a 2 in front of the, on the product side, 2 in front of this CO, and then 2 in front of the H2O.
Okay, so you're saying put a 2 here and a 2 here. Okay, so we do that. This is now.
How many O's?
Okay, so we have to adjust our O's. How many O's do we have?
5.
There's 2 times 2 is 4 plus 2 times 1.
6.
6, yeah.
Okay, so we have 6. So is there any way that we could get that balance over here?
Yes.
Since we have 4 over here.
Put a 2 in front of the O.
Okay, so we put 2 in front of the O. 2 times 2 is 4 plus 2. That's 6. That's a balanced equation.
Dr. Henry,
Yes.
the ones I'm having trouble with are when it's like turn 4 into 11, like the odd number ones.
Yes.
That's the one I'm having trouble with. I don't know if anyone else is. I just thought I'd say that.
Okay, so we'll do one more. We'll do one of those. Let's see. Oops, I should have kept that side.
Actually, I have one too after you're done with this one.
Okay.
Similar to the one you just did, but the numbers are different. So then the number is sort of getting really big.
Okay. So,
Carbon, hydrogen, and oxygen.
okay, so we have CHO. Okay, on the reactant side, how many carbons?
6.
Product side,
1.
1.
how many hydrogens?
12.
And product, how many oxygens?
2.
And product side,
3.
3.
okay.
Okay, I have a question. Like, I get confused. Like, where you were the one that we did before where you had to put like a 2 in front of like the C, and then where when you do the multiplication and then you add it, that's where I get confused.
I think that's what we're doing right now.
Okay.
Okay. So you're saying this is where we get confused. Okay, so if we have 6 carbons here and I want to get 6 carbons over here, so where do I need to put 6? How do I get 6
At
carbons?
the CO2.
Yes. So we want to put a number, a whole number in front of the coefficient. So we put 6 in front of it as our coefficient. Okay, so then that means that this means that we have 6 CO2 molecules.
Okay.
Right. Okay, so that means that CO2, 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 CO2. So that's what that actually means, right? So that means that there's 6 of those. So if there's 6 of those, how many carbons do I have?
6.
6.
6. Okay, how many oxygens do I have?
6.
12.
Or
Have-
that's where you multiply?
Yeah, because there's 2, right? There's 2 oxygens. So remember, this 2 refers to that oxygen. So there's 2 oxygens here. There's 2 oxygens here. There's 2 oxygen here. There's 2 oxygens here. There's 2 oxygens here. There's 2 oxygens here. So that's 2, 4, 6, 8, 10, 12. So that means I have 12 oxygens here, plus I have the oxygen here. So that's a total of how many? 13.
13.
Okay.
Okay.
Okay, so is that balanced?
No.
No.
No. Okay, so what do I need to do next?
Add a 6 in front of H. Hydrogen on the.
I switched the number here to 14, so that could be right.
Oh, for.
Yeah.
We can
It-
add a 7 then.
7. Okay, so I have a 7. Okay, so then that means I have how many hydrogens? Oops,
14.
14. Okay, so my hydrogens are balanced. How many oxygens do I have now?
16? Or no.
19.
I have 6 times 2 is 12,
12.
12,
plus 7,
19.
19. Okay, so that means I have an odd number, right? So this is where I would do my fancy work, since this is the only source of oxygen. I put 19 halves here. 19 times 2 is 19 halves times 2 is what?
19.
Okay, so would that be balanced?
Yep.
19 over here and 19 over there.
Yes.
Yes, but can I have a half a molecule?
No.
Right, so I can't cut Maria in half and say, okay, I'm gonna keep half of Maria and then I'm gonna give her the other half to her kids or her boo. I can't do that, right? Because then Maria wouldn't be alive, right?
Yes.
Okay, so we can't have a half a molecule. So then we need to set it up so we can get a whole molecule. So how can we get a whole molecule if we have 19 halves?
By multiplying everything by 2.
Yes, so we have to multiply the whole equation by 2. Okay, so if I multiply the whole equation by 2, we understand that this number here is supposed to be a 1. So it would be 2, C6, H14, plus 2
19.
times 19 halves. Is that true? We're making it up. Are you there?
Yep.
Dr.
Yeah.
Henry, did you do
Yes.
19 over 2 because oxygen has 2 molecules right there? So if
Yes,
oxygen
because
had,
yes, because there's 2 oxygens in oxygen gas, right? So the 2's will cancel out, right? So 2 times half or half times 2, it cancels each other out. So I end up with just 19.
so if that was like a 3 or something else, that would become the denominator?
That
And then
is
we
correct.
Multiply the whole equation by that?
That is
Okay.
correct.
All right, thank you.
Yes, I'll put a question like that on the next test.
No, that's okay. I think I got it.
You got it? I'll use ozone. Okay, questions, concerns, catch. So I multiplied this whole equation by 2, right? So this is understood to be 1. 19 over 2, that just gives me 19. 2 times 6, 12. What was that? Are you there?
Yes.
And 2 times 7, 14.
14.
Okay. Are you good?
Yes.
Okay. Not too hard?
That's pretty easy.
Okay. Heather, you had a question.
Yeah, I'm just contemplating if I want to have you work it or not because it's similar. The numbers were different, so I probably won't.
Okay.
I won't waste your time.
Okay, it was just a bigger one, right? Like
It
one
is
of
a
the tests.
larger one, yeah. And I was wondering if I got it right and it marked it wrong.
Okay. Well,
So,
I'll check. There's
I'll
a
wait.
possibility that you got it right. So,
Yeah. Okay. Thanks.
okay. Okay. So last we left off, we were talking about isotopes. You guys remember that?
Yes.
Yes.
Okay. So, and we said that an isotope is basically it's atoms that are the same element, but they have different masses. And their mass is going to change as a result of what? You guys remember?
Neutrons.
Neutrons. That's correct. So the example I gave you was, I think I gave you carbon 14 and carbon 12. Maybe. Oh, hold on. You guys see my little screen? Not mine.
No.
Okay, how about now?
Now we do. Yeah.
Okay.
PowerPoint.
It was blank.
You see a blank?
You gotta open your eyes.
It was blank.
Oh, okay.
That was good.
Okay, clear. Okay, so so this number here is called the what number again?
12, carbon 12.
Well,
Wasn't it the mass number?
that's right. It's called the mass.
Oh, I'm so sorry. That's my bad.
That's okay. So these are called the mass numbers. So carbon 12 tells me the mass of carbon 12. Carbon 12 weighs how much? Are you there?
12.
12. That's right. So it weighs 12, right? And so mass number
Is 14. Oh, wait.
so this one will be 14, yes. Mass number will be equal to the number of protons
Neutrons.
plus neutrons. Okay, how do I determine the number of protons?
By what element it is?
By what element it is. Okay, so we have carbon here. So let's look at, I'm having a little trouble here. Hold on. Let's pull up the P table. Maybe. Okay, so we pull up P table. And we see carbon. Oh, carbon's right here. So how many protons does carbon have?
6.
It has 6. What is that number called?
The element I.
The atomic number.
It is the atomic number. That is correct. Good job. El fuego. So that is our atomic number. Atomic number tells us the number of protons. So we know that we have 6 protons. If the mass number was 12, then how many neutrons would we have?
6.
Okay, so then we'd have 6 neutrons. Okay, if the mass number was 14,
3.
That would be 8.
8. That's right. Okay, simple.
So far.
Okay. Okay. Let's see. Here. Okay, so this is one of the common ways that we show isotope. Okay, so C12, 6, and so the 12 represents the mass number. This lets us know the atomic number or the number of protons. Okay, and so you'll see it this way, and you'll also see it the way that I just wrote it as well, where they don't include the atomic number, because you can look at the element, and it typically will tell you. So you'll see it this way as well. Okay, and then sometimes you'll see it written as this way. It'll be written C12, or they'll say carbon 12. Okay, questions, concerns? Cash?
No.
Okay, good. Okay, so what I'm gonna have you guys do is, I'm gonna have you guys get in groups, and then I'd like you guys to fill out this table for me. You guys can do that? We'll give you,
Yep.
say, 10 minutes. Okay, so take a picture of the table. Do you guys remember how to take a picture?
I forgot.
So if you go to annotate and you hit save, and then if you, it'll show up in your little screenshot here. Let's see. Okay. Okay, are there any questions? No
No.
questions?
Nope.
Okay, so I'll put you guys in groups. We'll see how you guys do. So we'll say group 1. So that would be Egger's group. You guys, can you guys do the first half of, since we have 7 groups here, so I'll have you guys do the first half for this part here, group 1. Enter your data, and then group 2, you guys do this part here. So this guy will be group 3. This is group 4. Group 5. Group 6. Group 7. And let's see. And then we'll do group 1 again. Let's see. Oh, let's see. I guess I should tell you group one. So group one was, I said Edgar's group. Group two was Jose's group. Group three was Sienna's group. Group four was Christina's group. Group five was Yari's group. Group six was Allison's group. And group seven was Alan's group. So, okay, looks good, looks good, looks good. See PV. Okay. So I have a question about this one right here. Let me use a different color. This guy.
I honestly don't know why I put 125.
And then this guy right here. Let's see the math.
We didn't get this far, so I was trying to figure it out right now.
Okay.
The neutron should be 124, and then the nuclear symbol should be 206 at the top.
Ah.
Let's see. So that's an 18. That's an O that looks like a D. Okay, looks good, looks good. Looks good, looks good, looks good. Okay, piece of cake. Okay, so if we have the value of the element, so we say just oxygen, oxygen alone, we know that oxygen alone, if we look at the periodic table, is 16, right? So its mass number is 16, and its atomic number is 8, right? And so we know that this would be the element, and then this would be an isotope of that element, right? So you're able to distinguish. Is that correct? Yes, no, maybe?
That's the thing that kind of confuses me, the whole isotope.
Yes. So again, isotopes are, they're, see, how do I describe this? So the isotope is basically an atom that is exactly the same element, right? So for instance, this is oxygen 8. So it just weighs differently than what we see on the periodic table, right?
Okay.
Yeah, so this guy normally is 16, right? So in other words, what you see on the periodic table is basically tons of them are 16 and only a few of them are 18, okay? So it's closer to 16. And we'll be talking about this in a second.
Okay.
Okay, so the distinction between them is just one weighs more than the other. And the reason why one would weigh more than the other is because of the number of neutrons.
Okay.
Okay, because the atomic number is always going to be the
It'll
same.
be the same. Yep.
Yep. Okay. Okay. So that basically disproves. Remember when I said, oh, you remember Dalton's law, Dalton's law? So that disproves a couple of things. One, atoms are not indivisible because we can break them down into subparts, electrons, protons, and neutrons. So they can be broken down into smaller things, and we can kind of use those things to kind of build new atoms, right? Unstable atoms, but new atoms nonetheless. And then all atoms of an element are identical. Well, we know that isotopes, right, are different because they have different masses. Okay? Questions?
Nope.
Good. Okay, so, and so that brings us to, we talk about our atomic mass. So the atomic mass is basically based upon carbon-12. And so the atomic mass actually represents the mass of the atoms of each element in comparison to each other. So of their isotope. So what you see on the periodic table is actually the relative abundance taken into consideration of each of the different isotopes that exist for that particular element. Does that make sense?
Yep.
Okay. So let me kind of put it down in another way. Let me put it in figure. So if we had carbon-12, we had carbon-13, and we had carbon-14. Okay. So I'm just going to put that 6 here. So in real life, technically all of these guys would exist, right? But since the weight of it is about 12, it's like 12.001. So then you're going to have like 99% is going to be this. We're going to say 0.2% is going to be this. And we're going to say 0, actually it should be 0. Switch these. Okay, so if we had took all the carbon, right, and we sit there and we had 100 carbon molecules, 99 of them would be carbon-12. Only 0.8 would actually be carbon, and only 0.2 would be, carbon-13, and only 0.2 would be carbon-14. So you get that?
Yep.
Yeah.
Okay, good. And so what you see on the periodic table is just the average of them based upon the abundance.
Makes sense.
Okay, so here's an example, a more concrete example, more accurate example. So here we have this is basically a mass spec of neon. And neon is able to identify isotopes. And so this lets us know the relative abundance. So this guy is about, say about 90-ish. We're going to say this is about 8, and this is about 2. Okay, so if we assume that there's about 2% of neon 21, we have 8% of neon 22, and we have 90% of neon 20. So if we went and multiply 90% times the weight of neon 20, which we're going to say estimate to be about 20. So 90% times 0.9. What's that? 18, something like that. I don't have my calculator. Where's my calculator?
$20 times 9 would definitely equal to 180.
20 times 0.9, sorry, that is a point.
Be 18.
It is
Okay.
18.
And then if I do 8%, so that's 0.8 times 22.
17.6.
Should it be 1.1.76?
Yeah.
Okay. And then if I do 21 times 0.02.
0.42.
Okay, so we add those together. Of course, the battery's dead.
20.18.
So 20.18. If you guys look on the periodic table, let's see. Neon. Ooh, look at that, 20.18. You guys see it? Good, bad, or ugly?
Whoa.
Okay, so piece of cake? Yeah, no, maybe?
Kind of.
Maybe.
Okay. So let's do another one real quick. Okay, it says the natural distribution of the isotope of boron is 19.9%, and it's boron 10 at a mass of 10.0129370 units, and 80.1% of boron 11, which is at 11.0093055 units. Calculate the atomic mass of boron. So how will we go about doing that? Any guesses?
You're given your percentages.
That's right, we're given our percentages.
And so what decimal would you multiply them by? Or
So our percentages are just going to be our decimals, right? So we're going to say 0.199, right? Times, this is the mass of this isotope. Ooh, sorry. I don't know what happened. Sure. Okay. You know, all my stuff. Okay, so as I was saying, oh, you guys are seeing my small screen, right?
Yeah. So we would multiply those numbers, right?
Yep. So you're gonna go 0.199
times 10.0129, and that's gonna give us the percentage of that one.
It's gonna give us, yeah,
number, yeah.
The relative abundance of it. Yep.
And we do it for each one. Then when you add them up,
it should add up to the molecular weight. That is correct.
That makes sense, no?
Yep.
Wait, so why did you make it 10.001, Dr. Henry?
Oh, sorry, because I am sometimes mentally challenged.
No,
I just added another 0. Good eye.
So when we did that first example, you just randomly put those numbers, right? That 0.2 and 0.8. That wasn't like exact, but it was
that was just based upon the graphs.
Yeah.
Yep.
But this is like this is how we're gonna see it normally. 10.
Yes, you're normally going to see it this exact. Yeah.
Okay.
Normally. Okay.
Mhm.
And then let's see, we have the 0.801 times 11.009305. Okay.
I have a question, Dr. Henry.
Yep.
So why are we multiplying the abundance of boron 10 to the mass unit?
Because this represents the mass of boron 10. That's how much boron 10 actually weighs.
And what is that giving us?
That's giving you the atomic weight, or it's giving you the percentage of the atomic weight of the entire atom, like of all of it together. So like, let me see the best way of explaining this. So this here represents the abundance that's found in nature, right? And so they want you to calculate, based upon the abundance found in nature, the atomic mass of boron, right? So if the majority of boron is boron 11, but you have about 20% of it is about boron 10. So when you're collecting boron, you're going to have an average. It's going to give you an average mass for it. It's not going to give you the exact mass of boron 11 because you have both boron 10 and boron 11. Does that make sense?
Yes.
Okay. It's kind of like so M&Ms, right? You guys have M&Ms? Anybody eat M&Ms?
Yes.
Are they all the same color?
No.
No. So in theory, there's a fraction of each color that's in there, right? Mm-hmm. So that's each of those colors are kind of like an isotope, but altogether they're M&Ms. And if in theory they technically will weigh exactly the same, but let's say one dye weighs more than the other, but it's really close, it's still going to weigh. You're going to have an average weight. You're not going to have the exact weight of that one that's of a particular color. Does that make sense?
Yes.
Is that why mine say 10.81 for the boron weight?
Yes. So that's why yours says 10.81 for the boron weight. Does yours say 10.81? Yeah, that's the reason why. Because if you actually multiply these together, right? So you go ahead and multiply these together, and you're going to get what, 1.99?
That's correct.
So just take fakes, yeah. And then this guy is going to give you what? Let's see. So this guy is going to give you 8.2. I'm sorry, 8.82. So 1.99 plus 8. We add these two together. So then that's 1, that's 8, and that's 10. So yeah.
Oh, okay. I get it now. I get it.
Does that make sense?
Yep, that makes sense. Thank you.
Okay, so now this here represents what you're going to see is, as I said, is the natural distribution of the isotopes. So in real life, we have those, each of those isotopes exist. You have the 10, and you have the 11. But 10 is only 20%, roughly 20% of the total, and 11 is 80% of the total. Okay, so that's the same thing with each element. So here's another example with neon. I mean, not neon, with lithium. So I won't go over this example since I used the example for neon, but you guys can kind of say this for yourself because who knows, you may see it on a test or something like that. Okay. Questions, concerns, Gash. Okay, so here, this here is just basically the percent abundance of some of the naturally occurring isotopes. And you don't have to know it, but you may be able to, you may have this table and you may have to calculate the abundance of certain isotopes. Okay? Or calculate the atomic mass of those particular atoms or elements. Okay, so in that case, let's say we're doing sulfur. So these are all of the sulfur isotopes. Okay, so if we're going to calculate the atomic mass of sulfur, then we'd have to take each of those isotopes in consideration. So then we'd multiply and this number by this number divided by 100. And anybody got a functioning calculator since mine is not functioning?
There right now.
Not right now?
I said I'll do it right now.
Okay.
Oh, never mind. Wait.
And take in consideration sig figs. Will make our lives a little bit easier. So this guy would be 31.97. Oh, should probably multiply this by something. Four. So 30.35. Okay, what about, so we divide this guy by 100. So then that's 32.971485 times 0.0076.
0.25.
0.25. And then the next one. Yes, oops, crap. So yeah, so we're dividing it by 100 so that we can change our percentage into a decimal. So the charity, is that what it is
0.26.
Yeah, for silicon 34.
Sulfur 34?
So sulfur.
Yeah, you said 1.46.
Yep.
And then the last one. Okay, so you had 0.0072. Okay, so we add these together. So we draw a line for sig figs. It goes something like this. Okay, so we have 7.2. That's 6. Zero point 32. Or 32.07. Okay. Questions, concerns, cash. Get our units. Are you guys there?
I am.
Yeah. Yes.
Yeah.
Okay.
Yes.
So does that make sense? You guys see the math and you see how it works?
Yeah.
Okay. So Dmitri Mendel and Luther Myers, they basically kind of organized the periodic table. It was a hot mess. So initially there was no real arrangements initially. And then at the beginning, there's a lot of errors that were associated. Okay. So then they started organizing it based upon the atomic number, which makes sense, right? So this is the organization of the periodic table. Let me get my P table. It's so much clearer here. Okay, so this is the organization of the periodic table. As we've talked about up here, these guys are called your groups. The numbers up top, that's your groups. These guys are called your periods. Okay, so when I took chemistry, the periodic table looked like this, where we have what we call the main group, which is, this is why you have the 3A, 1A, 2A, 3A, 4A, 5A. So that represented the main group. And basically the 3B, those were not the main groups, those are like just backups, because we didn't know a lot about those metals at the time that we knew about them, but we didn't know as much about them as we know now. And so we distinguish between the main group and the minor group. And so you'll see some of the older periodic tables, they'll actually have the 1A, 2A, 3A, in addition to having the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, defining each of the groups. Okay. And you guys have already been familiar with the, you're learning the differences between them, the metals, the non-metals. So these are all of the metals on the periodic table. You can see that a lot of them are metals. These guys are metalloids. They're like, they're in between a metal and a non-metal. These guys are all non-metals, okay? And these guys are your noble gases. And then you have certain metals that have certain characteristics. These are called alkali metals. These are called alkaline metals. Alkali metals are more reactive than alkaline metals. And we'll talk more about that later on, okay? So back to the lecture. You guys are familiar with the atomic number. You know about the chemical symbol, and you know about the atomic mass. You know how it plays. Groups, we'll often call them chemical families. They kind of behave the same, right? The ones that are kind of like right in line together. So group 1, the guys in group 1 kind of behave very similar to each other. Except hydrogen is kind of an oddball on certain ways. But these metals are, as I said, they're more reactive than others. So these metals are kind of alike as well too. They're kind of like a family. These are called halogens. These halogens are very reactive as well. They behave very similar. See? Okay, and then we already talked about periods. Periods are going across. We've talked about the main groups. So we have what we call transitional metals. These guys in pink, these guys are transition metals. So these metals, they're going to be a little weird, and that's why I say they're like transition. So they're going through changes, so they can have multiple charges associated with them. And some of them are there'll be a certain charge associated with some of them, like the majority of the time, but in theory, they can have other charges that'll be associated with them when they form ions. We'll talk about what an ion is here in a second, okay? So again, transitional metals right there. And then we've talked about these guys here. These guys are called post-transition metals, okay? They're also metals, but they sometimes will behave a little awkwardly, depending on who they're paired with. Okay, so we have metals, we have non-metals, and we have metalloids. Okay, so let's see how much you guys remember about the periodic table. Okay, list the atomic number, the chemical symbol, and the atomic mass of the third period element in group 6A/16. So remember, 6A makes reference to the main group, or you could just say group 16. So third period, group 16. So who's in the third period and group 16? Let's take a look.
Is it sulfur?
That is correct. Sulfur is the correct answer. I use another color than green. Okay, third period, group 16. Piece of cake?
Yep.
And its atomic mass is 32.06. Its atomic number is 16. And you guys can tell me how many electrons it has, right? How many electrons does sulfur have?
16.
How many neutrons?
It should be 16.
Okay. Good job. Are you guys all with me? Did I amaze anybody? My magic tricks.
We're with you.
Good. Just get so quiet. Okay. Okay, let's see. So look at the periodic table and let's see. Okay, so I'm not going to have you guys name as many. So I give you guys the periodic table because I believe that the way that you learn it is by using the periodic table rather than memorizing the elements. But there are ones that you should know, like the back of your hand, like nitrogen, carbon, oxygen, fluorine, chlorine, bromine, iodine. And you guys also know that those are diatomics. You guys remember all the diatomics, diatomic elements?
Wait, can you say that again, Professor?
Diatomic elements, do you guys remember? Have no fear, exactly, Ms. Torres. Have no fear of ice cold beer, right? So if we have no fear of ice cold beer.
Hydrogen,
So we have hydrogen,
nitrogen,
nitrogen,
fluorine,
chlorine,
oxygen, iodine, chlorine, bromine,
Carbon.
not carbon,
fluorine,
fluorine. So there's 7, right? So it's hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So those are your diatomic elements. Okay. So you want to remember those because you know that those guys, when they're by themselves, they're going to form a molecule that's diatomic as an element. Okay. But the ones that you should be familiar with are like these guys here. Let me just draw my board. And then other ones you'll start picking up. But you should at least know these and your noble gases. Now, you don't have to memorize them. You have your periodic table. Your periodic table is always going to be available for you. Okay? Okay, so naturally occurring lithium is composed of two isotopes, 7.59% at 6.01512224 and 92.4% at 7.01600041. Okay,
Right.
so what are we going to do?
So I understand that we're going to multiply those together and then add them. My question is more of where do we get this information off of the periodic table?
So it's not provided to you on the periodic table. You can find it on P table by clicking on it. So they're not going to give you each of the isotopes. So you would get a table normally that's providing that. So
okay.
I can show you. Hold on.
That was my only confusion because the table I'm looking at doesn't provide like the percentages and whatnot.
Yeah, it gives you just that average. That's all you get.
Okay, yeah, no, I'm good then. We can move on. My bad.
Okay, no worries. No, but that's a good question.
I just thought I was missing something. That's all.
Nope, you're good.
All right.
Okay, let's see. Okay, so we're going to go to chapter 11. Okay, so let's see. Maybe. Okay, so we're going to talk about atomic theory. And we're going to go over it pretty fast. But there are a couple of things that we're going to first talk about. First off is electromagnetic radiation. Okay, so basically light is a form of electromagnetic radiation. White light, as well as gamma rays, X-rays, UV light, infrared light, microwaves, radio waves. So all of those guys are examples of electromagnetic radiation. And the thing is that they're like forms of energy that behave in a wave particle duality. So they exist in both forms, both the wave part and a particle part. So things that you want to know and you want to keep in mind, energy basically is transmitted at the speed of light. So, and that's 3.0 times 10 to the 8th meters per second. And again, it's in a wave particle. So it's just like a wave. Can you guys see my screen? Is it showing up?
Yep.
Okay, I just want to make sure. Okay, so since it's a wave particle, we have what we call the wave equation. And we basically will say that the speed of light is equal to lambda represents the wavelength. And nu, this is nu, it's not a V. As in like I have new shoes, but it's NU. Nu is frequency. So lambda is wavelength, length. So we measure length in what type of units? Give me an example of units that we measure length.
Miles, inches, length, right?
Yep, that's right. Miles, inches, meters, millimeters, micrometers.
Feet.
Well, feet, yes. Feet. Okay, so we know that this is a length. So we know that that's going to be one of those type of units. So we want to keep that in mind. So nu is 1/2 or we often will call that hertz. Okay, so you'll see it written as Hz for hertz. Okay, so, and that's for the frequency. Okay, so we know that the speed of light is a constant. So it's always going to be 3.00 times 10 to the 8th second. The wavelength could actually let us know a couple of things, because certain lights have different wavelengths. So you guys did the spectra analysis, right? Yes, no, maybe?
Yes.
Okay,
Yes.
good. So let's see if I can pull this up. Okay, so this here represents the light spectrum right here. So from 400 to 700, that's visible light. So all together, all of these different colors all together make up white light. Okay, so this represents, this band right here, basically represents all of white light, but we can sit there and diffract them into their each individual components. So that's what you guys did with the diffraction slide, or your spectrometer, right? So you basically broke up white light. So did you guys, when you guys broke up the sun rays, what colors did you guys see?
The rainbow.
You saw the rainbow, right? And so you have each of those. And so each of those basically, so blue has a different wavelength that's associated. So it's a wave. And so the wavelength is basically the distance from peak to peak. So it'll be like here to here, or trough to trough. So that is going to represent your wavelength. Okay. So blue light is about 400, or purple light, or violet is about 400 nanometers. Blue is about 450. Green is about 500 to about 550. And then you have yellow, orange, and red. Red is about 700. Far red is about 700. Okay. So since we have this equation, C equals lambda, lambda being the wavelength, times nu, like my new shoes, which is the frequency. So as the wavelength increases in size, what will we expect the frequency to do? Would we expect it to get higher or lower based upon proportionality?
Lower.
Okay. So that's right. So as frequency increases, as wavelength increases, we would expect this guy to get lower to balance it out, right? And so as we look at this, so gamma rays are the smallest, and then X rays are a little bit bigger, UV rays are bigger. And so as these guys increase, we'll notice that the frequency decreases. Okay, make sense?
Yeah.
Okay.
Yeah.
Okay, so now to kind of give you perspective, right? The size of an atom falls somewhere in here. So it's between that 10 to the minus 10 meters, right? To the size of a virus, which is around 10 to the 8th, right? So atom, this is where a virus falls, bacteria cell, animal cells, right? Then we have the thickness of a CD is here about the distance of a wavelength or a microwave. The width of a CD, still in that microwave range. The dog is about the size of the wave for the FM radio. You guys listen to radio? You guys probably don't know what radio is anymore, right? You guys all use Spotify or
Listen to it.
yeah.
Radio.
Okay. So to kind of gives you an idea of how far that wave is, you know. So if it's the size of a dog, it's far, you know, pretty far. Okay. So we have continuous spectrums and we have what we call lines. So when you guys had that rainbow flowing together, that's an example of continuous spectrum. Okay. Now line spectrum, so you start seeing specific lines. So if you guys had looked at LEDs or the same element, you guys would have very specific lines that are shown. Okay. And so that would be your line spectrum. And I'll show you an example of that. These are also called discrete lines because they're literally separated. So you'll have colors of line that'll be separated from each other. And so each element has a discrete line spectrum. So it's not necessarily going to flow all together. You're going to have very discrete lines that represent particular elements. Okay. And the reason that they have discrete lines associated with them, and I want you to kind of think about it, is because we're actually looking at the energy that's going to be released by electrons after we get them all excited and worked up, okay? And so that energy that is typically released by these electrons, they're called photons. You've heard of like a photon gun? Yeah, good. Okay, so this is just basically showing you wave properties. So this is the wavelength, so from peak to peak, or as I said, from trough to trough. And so these two waves have two different frequencies, right? So frequencies are just like the cycles of a wave in a given time period. So in this given time period, like basically from this barrier, right? So we have this one wave which has one wavelength, like, so you'll have one complete wave, where this one has 1, 2, I say 1, 2, 3. So you'd have 3 waves that would fall into here. So you'd basically have one-ish that would fall under there. So the frequency of this guy, which frequency is greater? This one or this one? A or B? Frequency, that's great.
A.
Did you say A or did you say B?
A.
Not A, B. So B would be the correct answer, right? Because we have 1, 2, 3, 4 peaks, right? So that lets us know that that would be 4 compared to 2 peaks here. So this would be a smaller frequency, bigger wavelength, but smaller frequency. This one would have a larger frequency, but smaller wavelength, because they're indirectly proportional. Sal, you can't say both.
Yeah, I typed in the wrong thing. My bad.
Okay, so here, this is basically white light. This is basically showing you that beautiful spectra that you guys all saw. So this here is an example of hydrogen's specific spectrum, specific line spectrum. And so again, it's going through your spectrometer. And so you can kind of see that it's 4 different discrete lines that are showing up. Okay, so this is a real spectrum from this is hydrogens, this is mercuries, and this is neons. And so do they look alike?
A bit.
A bit?
What
was that?
Not really.
No, not really, right?
No.
So hydrogen has 4 that you can see, 4 very discrete lines. You have a blue, cyan, lime green, and red, right? And where mercury has 2 blues, 1 cyan, 2 lime green, and 3 yellows. And so they're very discrete in terms of what they have. And I'm going to ask you, why do you think they're so discrete from each other? Why don't they look exactly alike?
Is it because they're different elements?
Well, it's because they're different elements. So what did I say about the light is actually representing energy coming from where?
From light?
Light is energy coming from, I said, light is energy coming from where?
Oh, the sun.
Through sun?
No, so in the case of these elements, right? So they'd be energy coming from what? What do you guys think they're coming from?
The glow stick? I don't know.
I said it earlier. I'm just seeing if you guys were listening to me. Obviously not.
Is it the wavelength or the frequency?
So wavelength and frequency are modes of delivery, but what's providing this energy? What is storing up this energy and is releasing this?
Photon?
A photon, yes. So a photon is that form of energy, right? but it represents the energy that's being released by electrons. Okay, so photons are just energy released from an electron. Let me show you. I'm gonna skip this a little bit and go somewhere. Okay, so what happens is electrons exist at a ground state, at a normal level. And how many of you guys have kids? Anybody have kids?
No.
I do.
You do?
Me.
Okay,
Yes.
good. So, in the case of your kids, if you feed them a whole bunch of sugar, what happens?
They get too hyper.
They get hyper, right? So they just get really, they're just like, oh, bouncing off the walls, right? So in the case of these electrons, if you feed it energy, it's going to be like your kid, hyper. It's going to go from that excited, that ground state to an excited state. So then they're just so excited, they're just doing everything. They're just bouncing off the walls, they're running everywhere, right? So then what happens at the end of the day?
They fall asleep.
They crash, right? They crash hard, right? So that's the same thing that happens to the electron. But when the electron crashes, it releases a photon. It releases that energy. Okay? So just like in the figure. Are you guys with me?
Yeah.
Yep.
Okay. So they differ because they have different numbers of electrons, right? And so the energy states are going to be different for each of those. And we're going to talk about that a little bit. So Bohr was this, really great scientist that he's kind of like the father of quantum mechanics or quantum chemistry, okay? And he modeled his theory around, around the hydrogen atom, okay? And so he's basically said, okay, so these electrons, they get excited, and then they could go up in energy, right? And so he had done the work and everything like that, and he basically said, okay, so this is how it really works, is that, this is an example of the continuous spectrum, which is running into each other. But he says it's not really like that. These electrons are kind of act like steps. So you have like energy steps that you have to go through. Okay.
Let's go.
What was that?
Oh, sorry. I was talking to my dog.
Okay. So here, this represents the nucleus. This represents that first energy step. So that first ground step. So this is where, for the hydrogen atom, this is your ground state, your N equals 1. So that's your ground state right here. So in theory, we can put energy in there and we can make it go up to ground state 2, that next orbit, or we could put more energy in it, make it go up to that third orbit, or we can put more energy up in it and go up to the fourth, okay? And so by putting energy in, we're sitting there putting it to another energy state. We're exciting it, okay? And then once it gets excited, it's gonna crash and it's gonna let loose that energy. And that's the light you see. So have you looked at fireworks?
Yeah.
Okay, so like, are all the fireworks the same color, or are they different colors in the sky?
Different colors.
Different colors.
Different colors.
So what makes those things different colors is the fact that each of them are different elements. So you're putting in that energy, right? When you light them up, and then they go shh, and then they blow, right? You're letting loose that energy. That energy starts dropping. So you see those photons. So you see those green photons if it's barium. You see orange if it's sodium. So you'll see different colors based upon the different element it is. Okay. So quantum jump or leap is just that leap to that energy level. Now, they've never been able to see a measurable passage that gets the energy level. It just shoots up there, right? It just shoots up to that level without going to that next step. It doesn't have to go in between. It can just go up that level. So that's considered your quantum jump. There's a whole show called Quantum Leap that was based upon, jumping through time as a result of that energy. And as we said, we talked about ground state, we've talked about the excitants. So, are you guys cool with the whole concept of quantum so far?
Yeah.
Okay.
So the color that we see, is that the end step, the release?
Yes.
Like when it
so,
meets the final?
exactly.
And you're saying that they haven't been able to catch like the different levels.
Well, let's see if I have it. I have to remember which course, because I have different figures for different courses because there's levels of knowledge. I don't. In the case of what you're saying is, so like if we talk about the energy levels, right? So what I'm saying is that we can excite this one electron, which is normally at the ground state, this ground state level. So I can excite it all the way up to the third level. I don't have to go through each of the different levels first. I don't have to go to the second level. I can just put the energy in. There's no passage for me to actually have to go to the second level. Okay. Does that make sense? So it just, you put the energy in and it just shoots up there. You don't see it go, you don't see it shoot up there. You don't have to go to the next step to get there. I guess it is showing up here. So,
Dr. Henry?
Yep.
Are we ever gonna talk about orbitals and like the electron configurations? I was looking at that in our Chem 101 homework and I don't know.
Don't get intimidated. That's what we're getting to right now, right? So what Bohr basically decided, he basically said that there are different energy levels. And so each of those energy levels represent what we call one of our quantum numbers. So, or represents our principal quantum number. So the principal quantum number N represents the period that's running. So if we're talking about our, oops. Sorry. Our table here. So period 1, period 2, period 3, period 4, period 5, period 6, period 7. Each of those represents an N value. They also represent the energy that's associated. Okay, so 1 would be the ground state energy, particularly if we're talking about hydrogen electron, right? And so the N value for the quantum number is the period, essentially.
Say it again.
The N value is essentially the period.
Okay.
Okay, so we have what we call the principal energy level, which is going to be our period. That's going to be our N. The sub-level is going to be our S, our P, our D. And I'll kind of work those through with you. And then we have what we call the orbital. The orbital, I'll kind of explain that. And then we have the number of electrons in the orbital, which is often referred to as a spin. Okay, so we have a positive spin and a negative spin in each orbital. Okay, so you have 4 quantum numbers: the principal energy level, the sub-level, the orbital, and then what we call the spin. Okay, so N could basically go from N equal 1 all the way up to infinity, right? On our periodic table, we're limited to only go to 7. But in theory, we can go beyond 7, right? Because there's a possibility that we'll discover more and more elements. Okay. So the sublevels, or the subshells, that's called your S, your P, your D, and your F. So let me show you what your subshells are represented in terms of your periodic table. Your periodic table basically contains most of the stuff that you need. Right here, this guy would be your S orbital. This guy, your S subshell. These guys over here, these are your P subshell. This here is your D subshell. and this here is your S subshell. Okay, so these here, these last two here, these guys are really just placeholders. They're part of the D subshell. These guys are really Ds. Okay. Are you with me so far? Okay.
Yep.
So
Yeah.
the S subshell can only hold 2 electrons. How many groups do we have here?
2.
2. Okay, the P subshell could only hold 6 electrons. How many groups do we have in the P?
6.
The D subshell can only hold 10 electrons. How many do we have in the D?
10.
10.
And the F subshell can only hold 14 electrons. How many do we have in the F? Now remember, this guy's a part of the D.
$14.
14. Okay, so the periodic table is kind of organized the same way that our electron configuration is. It lets us know. So when we're talking about an element, and we're talking about the electrons in an element, each element has so many electrons, but each of those electrons in the element have a different set of quantum numbers that are associated with it. They're located in a different spot, okay? Because you're talking about each individual electron. And so what we're going to do is we're going to actually keep track of all the electrons. What we're going to do is called electron configuration. And I'm going to show you that process of figuring out the electron configuration. I'm going to show you a very simple way of doing it. Then I'll show you another way of doing it as well too, because there are exceptions. And those exceptions you would have never guessed. You would expect it to be one thing, but you'd end up being something else.
Wait,
Okay.
Dr. Henry, can you repeat the number of electrons in the subshell for each category? It's
Sure.
kind of hard to read.
Okay, so let me put it in the corner here. So we have S has 2, P has 6, D has 10, and F has 14.
All right, thank you.
Okay, so now the thing is that the periodic table is limited because by the number of elements that we actually have. We know that we're probably going to discover that there are other elements that exist that we just don't know about at this point. And so we've given room for growth for the periodic table and also room for growth for our subshells. So after F, we would go G, then we would go H, then we would go I, then we would go J. So based upon this trend, how many electrons would you expect G to have?
18.
And then what about H?
22.
And I?
6.
And J?
30.
And who is that?
Zamaya.
Good job, Jeremiah. Okay, so we have the ability to sit there and grow beyond what we see on the periodic table. And that's going to be kind of important because you're going to get a test question. Okay, so let's start talking about electron configuration. So if we were talking about, let's say, carbon, and we wanted to write the electron configuration, we would just go through and we would always start with the very start for the very first electron for carbon would be in the 1s. So 1s, and that would represent this guy, then we'd have 2 electrons. Then the 2s would have 2 electrons. And then how many electrons total does carbon have?
6.
6. So then we would get over here to the P, and then so we'd have 2p2. And so this would be the electron configuration for carbon.
Wait, is helium part of the S again?
Yes,
Okay.
helium is really part of the S.
Okay,
So
good.
technically, it's over here with this guy. Okay. So if we were talking about, let's say, aluminum, Al. How many total electrons does aluminum have?
13.
13. Okay, let me use a different color so you guys can see it. Or move it. Okay, so aluminum has 13 electrons. So again, we'd start at the 1s. Then we go to the next level. So that would be the 2s, 2s2.
2p6.
Then there's 6 here, so 2p6.
3s2.
3s2. And 3p1. Okay, so then that would represent that 1 electron that would be here.
Oh, Dr. Henry, I have a question.
Yep.
So I remember that the D group actually starts at 3.
That is correct.
So do we if we get to like maybe like I don't know like gallium, would we just put it to like right after 3p6? Would we do 3d10 and then 4s2 then?
That would be correct.
Okay.
Yes. So the d orbital actually starts at 3. The f orbital actually starts at 4. So this is 4f down here. Okay. So let's do copper. So we start off at the 1s, so it'll be 1s2. Then we go to the 2. So that's 2s2. Then we have 2p6. Then we have 3s2. Then we have 3p6. And then we have 4s2. Then it would be 3d, 1, 2, 3, 4, 5, 6, 7.
Wait, Dr. Henry, did you mean cobalt or copper? Because
I
you
meant
cobalt.
I meant copper. Sorry, meant copper, but I said cobalt. Sorry, I circled cobalt. Good eye. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Questions?
Yes, Dr. Henry, what's the point of this?
So the part of it is to kind of understand, it's going to help you understand what we call valence electrons.
Oh, okay.
So the electrons that are going to be able to be involved in bonding.
Got you. Thanks.
Okay.
I was just wondering why we were separating it like this.
Yeah. And then I'm going to show you another way of separating it, right? So basically we've already done aluminum and we've done copper. Although this electron configuration for copper is actually not correct because it's all based upon energy. At the end of the day, it's based upon energy, the amount of energy level it takes. And so there's another energy level that's lower than this energy level. So it will take that energy level down. instead. And I'll show you the electron configuration for that, just for kicks and giggles. But if you get this one, it would be okay. I'll accept it for the exam. But in reality, there is another one that would exist. So let me show you we'll start with aluminum first.
Dr. Henry, I have a quick question.
Yep.
So I just got a little bit confused there when you went 4s2. Wouldn't it just be 4d9?
For when we went 4s2 for, oh, no, it would be, it's 4s2 because this is the s orbital. This here represents your s orbital. Then it goes 3d.
Okay, so
this starts at the third energy level. So it's one off.
Oh, okay.
Yeah, I know it's really weird. So it's part of this, what they call degeneracy. It literally, it's one energy level off, even though it's a higher energy level than the 4s. So the way you're putting in your electrons, you're putting in based upon energy. And I'll show you that here in a second.
Okay, so that D column would always be off by 1.
Yep. So yeah, this will be 3D, then this is 4D, then this is 5D, this is 6D. So this is 5, so then this guy is 4, so off by 1.
Okay, got it.
Yep. And then when we get down to the F is off by 2. So if this is 6, then you go for F, right? And then you go, this would be 5D, right?
Yeah.
Okay. So another way that we could write this is by taking the noble gas. You guys remember the noble gases? The noble gas that would be before this element. So what noble gas is before aluminum?
Neon?
Neon. So we'd write neon. Neon would represent our core. And so what the core is basically they're electrons that are kind of protected. So you're not going to use those for reacting. And then you would just go after neon, it would be whatever it is afterwards, which would be 3s2. And then 3p1. Okay, so all of these electrons are protected. Right here, these guys are protected and they represent that core. So those guys can't be used for reacting. Only these 3 electrons can be used for reacting. Are you with me?
Yep.
Okay. So in the case of copper, right, if this was the correct one, we would write copper. Copper's here. What is the noble gas that's before copper?
Argon.
Argon. Okay, so then we go argon, then it'll be 4s2. Then 3d9. Okay, so these 12 electrons, 4s2. Let me fix that. That's horrible. These 11 electrons would be involved in bonding. Or can be involved in bonding. Okay, so these guys would be considered valence electrons. And then in this case, for aluminum, these guys would be considered its valence electrons. Okay, are you with me so far?
Yep.
Okay, is your brain fried yet?
Yeah.
A little.
Okay, so when you guys were sitting there with your glow sticks, so let me kind of pull some things together. So your glow sticks, when you guys had your glow sticks and they changed the different colors, you got a purple one and you had a green one and you had a, so you had all of these different colors. So what do you think is causing those colors to be different?
Probably the different chemicals inside them.
The elements.
Different chemicals, okay? So now let's get more specific. So what's causing those colors for different chemicals? So like, for instance,
The
more
energy.
than okay, so the energy what?
That's being released.
The energy that's being released, exactly. And so each element is going to have, well, most elements will have a certain color that's associated with it. There are some that you can't see any distinct color. It's really hard to see, or so, but there's going to be a color associated with each of the different elements. Okay, so like, for instance, barium. So the green ones are more likely to be barium because they're like a nice green color, right? And then the red one may be strontium, right? So depending on which element you're working with, you could have a different color associated with your glow stick, okay? Make sense?
Yeah.
Yep.
Okay. So we're going to stop here. I want you to kind of digest it. We'll go over parts of this again on Thursday, okay? Now,